All right, so over the next couple of days, we want to take a look at vibrations, both mechanical and electrical vibrations. So let's start with mechanical vibrations, namely springs. So here's the situation here. I've got a spring that has length little l. There are various forces that act upon, I put a weight on the spring and the weight gets pulled down. Put a mass on the spring, whatever you want to call it, and it gets pulled down. There are various forces that act upon this mass. The spring would be pulling it up, gravity is pulling it down, and we'll look at some other things that might be there too. In particular, I want to remind you of, or inform you of, if you've never heard it before, this thing called Hooke's law, which is right over here. If we stretch a spring a distance of x, then the force of the spring is k times x. Okay. I see this as in a fish scale. I was at a fishing derby one time, and you had this spring hanging there on a post, and they'd hook the fish on the bottom, and it would pull it down. And as it pulled down, there was a little needle that pulled down with it, and however far the needle went down was on a scale that told you how much the fish weighed. That is, the force or weight was proportional to how far it went down. It was a linear scale. So the force or the weight hanging on the spring is proportional to the distance that the spring gets stretched. At the point where the mass stays still, so the force of gravity is pulling it down and the force of the spring is pulling it up, if it's staying still, it means those forces are equally balanced and the net force is zero. So when the mass is at rest, mass times gravity, which is the force downward, minus KL is zero. Why do I have that minus instead of plus? Well, in magnitude, force times, yes, okay. Here's the way I'm thinking of it. That x is a displacement. L is the natural displacement, how far it wants to be at rest. Positive number, k is a positive number, m and g are both positive numbers. So let's subtract them to get zero here. Now, what are all the forces acting on it? What I'm going to do is I'm going to pull this down even further and let it go and watch what happens. So what are all the forces acting upon this thing so that I can describe its motion? Well, we already talked about gravity pulling down. Force of gravity is mass times acceleration. G is the acceleration of gravity. The spring constant, comes from Hooke's law here, that the spring is going to be k times the displacement. Well, we're going to displace the thing a distance u away, so you pull it down to a distance here u. The total displacement that it has is L plus u. I'm going to consider u being positive in the downward sense, okay, in the same direction of gravity. So this is positive. The spring, of course, would then be pulling in the opposite direction, where, so we throw a minus sign in here. Total displacement is L plus u times k to get the force, and it's upward, which in this case I'm calling upward the negative direction. So the force of the spring is upward. There also may be some damping in that if there was no resistance at all, when you let go, you can imagine what would happen, that this thing would just bounce back up and down. That's what springs do. But eventually they slow down, and they slow down because there's things happening. There's air resistance, there's within the spring itself, the flexing of it and the unflexing of it creates a little bit of friction and heat. That energy is lost. It slows the motion down. So there are some forces of damping here that are resisting the continued motion. Now, there's various ways that this is modeled for our purposes here, and a reasonably good model is to assume that the force of damping is proportional to the velocity. So if u is the displacement, then the derivative of u would be the velocity. And it is always in the opposite direction of the velocity. This is like air resistance. When you're flying through the air, it doesn't matter whether you're going up or whether you're going down or sideways, air resistance is pushing against your motion, against the direction of your velocity. So whatever the velocity is, you're going to multiply that by negative some constant gamma. Okay. And there may be some external force to this whole thing. External force would be if I were, you think about this thing bouncing up and down, but I had hold of the top of this spring and I was tugging it up and down too, sort of putting some other sort of forces into this. From the point of view of what we're doing today, we will have a zero external force. In the next section, next week, we will look at some positive external force, some type of external force, and see how that affects the system. Right? So, the thing about motion, motion in general, is that force equals mass times acceleration. Well, acceleration is the derivative of the velocity. So where u was being measured as the displacement, then u prime, which I talked about here, was the velocity of this thing, and u double prime is the acceleration. So the net force on this thing is mass times its acceleration. So as I look down at this thing and look at all the forces, I can say, well, mass times acceleration is equal to the sum of all the forces, gravity plus the spring constant plus any damping plus any external force. Okay. Plugging some things in here, let's see, gravity, damping, that was the spring, and the damping, and some external force, which might be a function of time. Again, we're gonna let that be zero, as you'll see in a moment. Let's see, multiplying stuff through, the minus KL plus mu looks like this, but the mg minus KL is zero. That's the, hey, when this is sitting at rest, that's zero. And what I end up with is mass times the acceleration minus gamma times the, minus gamma times the velocity minus k times the position plus there, moving stuff over the other side. I've got this second order differential equation in u, or mu, whatever that is. I guess it looks like a u. If this external force is zero, we have a homogeneous equation, and this is called free vibration. This is, as we'll see, that we get a vibration out of this, but there's nothing forcing it. It's free. If gamma equals zero, that is, there's no damping, we call this undamped vibration. So undamped free vibration if both gamma is zero and this function over here is zero. Okay. So let's let's first take the example where gamma is zero and you're looking at something like this. Right? This is second order, linear, constant coefficients, homogeneous. I assume an answer that the solution looks something like this. I plug it in here, and I get that r is plus or minus the square root of k over m times I, right? With k positive and m positive and a plus sign in between there. It becomes a minus when you take it over to the other side. Anyway, you're taking the square root of a negative, you get this imaginary solution for r, which means that the solution for the differential equation is actually a sum of sines and cosines, right? And the square root of k over m is determining how fast this thing is vibrating. There's an identity that we'll have to look at. I don't know if I want to do it now. We'll do it maybe in class, but maybe I do it right now. Yeah, I guess I'm going to do it right now. All right, let's see here. Notice this is a sum and sine of sines and cosine, but I want to rewrite it as simply the sum, as one cosine that's been shifted to see that this is just vibration, right? It's not any kind of crazy curve going on here. It's just a sine curve or a cosine curve. So I claim it can be written this way, which if you know any trig, and I hope you do, I'm essentially going to figure out what r is, the amplitude of this cosine curve, and how much it's shifted. Okay, so I'm claiming the sum of these two things is just one sine curve of maybe a bigger amplitude and maybe shifted over some. So working backwards somewhat, cosine of a sum is the cosine of the first, cosine of the second, plus the sine of the first, sine of the second. So I'm breaking this cosine of a difference here. It can be broken up this way. I then notice that, hey, when I multiply the r through here, that r cos theta is playing the role of C1 right there, and that r sine theta, sorry, not theta, that's a delta. R cos delta and r sine delta are playing the roles of C1 and C2. So I get these equations that R1 cos delta is C1 and R2 sine delta is C2. And this should look familiar to you because this is, well, this is polar coordinates, right? If this is C1 and C2 and R is the hypotenuse there, then this is precisely that relationship. So what I can see from this is that R is the square root of C1 plus C2, sorry, C1 squared plus C2 squared, and that that angle, delta, is the arctan of C2 over C1, right? This is an identity that this thing equals that is one that I never remember. First of all, it's a matter of, am I doing a cosine or am I doing a sine? If I was doing a sine, things would look a little different because this identity would look a little different, but the follow through would be kind of the same. There's also a matter of, is this a plus sign to start with? So does this become a plus sign or a minus sign? I figure it out every time. I know I can do it. I know that I can take something like this, a sum of a sine and a cosine with the same period. This number here is the same as that number there. It will combine together to be a single sine curve or a single cosine curve that looks like this. Anyway, I've got vibration. This is just a sine curve or cosine curve bouncing up and down when I had no damping. If you do have damping, then recall that what would happen is your solution would have, you'd have a real part here, and you'd have this whole thing times an exponential. So it would look like vibration, but with damped amplitude, right? So it gets smaller and smaller as time goes on. Anyway, the next thing we need to look at is some electrical vibration, and I'm going to do that in another video.